Hi, everyone. Thank you so much for joining us today for this combined session on designing sustainable urban land systems and mapping, analyzing, and modeling human settlements at a global scale. In full disclosure, the GLP Organizing Committee combined our two sessions for us, but in sort of review of what was submitted in terms of abstracts and what will be discussed today, it seemed like a really happy marriage. So I'm going to be, my name is Kelly Turner. I'm a professor of urban planning at UCLA. And I co-organized this session with Heather Sander from the University of Iowa, who unfortunately couldn't be with us today, and Emanuele Strano from Mind Earth. And so I'm going to give a brief introduction to the motivation for this session, which we hope to include all of you. We'll have a series of full and flash talks, and then we'll have a good chunk of time, hopefully at the end, maybe about 15 minutes for audience interaction and discussion. And it does matter what you say in that participation because we'll be typing up the notes and it will go into official GLP record. Then I'm going to give a little brief flash talk of my own and then pass it on to our wonderful presenters. So without further ado, what is the motivation for this session? Well, land system science really has to consider that now we're in the century of the city. This is a claim that's been made by many and evidenced, the importance is evidenced in recent special issues in science and the proceedings of the National Academy of Sciences. And the problem is that global urbanization is a central driver of land change in the 21st century, both sort of a local driving factor. We're expecting a doubling of the spatial extent of cities in the future, and also urban land teleconnection. So what happens locally in urban systems affects rural and sometimes distal locations. But how we urbanize matters, and this is where the design part comes in. Not all urban areas are created equal. So the solution is to define novel approaches to planning, design, monitoring, and evaluating this sort of urban land change. And so this session will address two interrelated challenges. The first has to do with bridging the gap between the land system science and design community, and the other has to do with addressing the urban agglomeration bias in land system science methods. Okay, so there have been calls for something called an urbanization science. The extent to which this is new, I'm not so sure, but it is a sort of this outcropping of sustainability science and the global environmental change community saying that we need new sort of theories and methods that are specifically around urbanization themes. And the common factor across all of these is that there's a strong transdisciplinary component, that we're not working just across different disciplinary communities, but also with those in public and private sectors. And so I just have a few examples of this. One of the older ones here by Nassauer and Optum about design and science, explicitly addressing the linkages between those two communities. There's this sort of renaissance in urban ecology of what used to be this distinction between ecology in and of the cities, and now is moving towards ecology for cities. And of course, a series of publications defining this actual sort of urbanization science agenda. So there's a sort of strong momentum towards doing urban work within the land system science community. But I'm going to argue that it's sort of a cause without a real tangible community. And the reason I say this is, so there have been some sort of disappointments in terms of our institutions that will help to build and forge that intellectual community. UJEC, the Urbanization and Global Environmental Change, community folded its doors. In fact, I think this reads kind of like an obituary here. Welcome to UJEC 2006 to 2017. Has been folded into Future Earth, but I would say the kind of corollary institution that we're all here taking part in, the GLP, has not folded its doors. Also, recently we got word in the United States that the Baltimore Long-Term Ecological Research Center, which is one of two urban long-term centers in the United States, was not funded for continuation. So I don't know where that leaves sort of the NSF stance on urban work. And then the direct motivation, at least for this first half of the session, came from Heather and I were attending the National Socio-Environmental Synthesis Center meetings. They had this boundary spanning symposium last summer. And one of the themes was socio-environmental systems by design. Unfortunately, there were only 2 to 3 presentations that actually dealt with design, and usually design was interpreted kind of loosely to mean things like institutional design, but not actually sort of the physical design of cities. And then in terms of sort of methods and methodological development, obviously land system science has a long tradition of kind of historically has treated urban as its own sort of land class, and urban is driving things like deforestation or environmental degradation. But with the advent of more advanced geospatial technologies and methods, we know that urban is actually more than one land class. And we can see sometimes, this is evidenced through things like Google Earth and other remote sensing products that can tell us with very, very fine detail, sometimes too fine in the case of the Google Earth nudes. But also understanding that these land classes themselves aren't maybe necessarily sufficient to tell us the whole story about what's happening in terms of urbanization. So a couple overarching questions for us to consider as a group today as we think about the talks we hear. The first is, what is the role of land system science in shaping cities in the 21st century? And this relates sort of to that design element, that interfacing between public and private sector. What are the methodological, institutional, epistemological, pragmatic, and normative challenges that we encounter in our work? I'm sure we can kind of share some war stories from the field. And then how can we overcome those challenges? What are our creative solutions? So with that, I'll turn to a brief example from my own work which motivates these sort of questions. And in this, I'll provide a brief overview, very, very brief overview, and then turn to sort of what are the bigger picture problems that I've encountered in this work. So for a long time, I've been working on the issue of microclimate regulation in new urbanist communities. For those of you who aren't familiar, new urbanism is a design movement that promotes, among other things, compact design, densification, and urban greening. And it explicitly now has adopted a climate change addendum where they outline environmental goals related to climate adaptation, amongst which is microclimate regulation. So I've been working in this community in Tucson, Arizona, in the middle of the desert. It was a large planned community. It was built in 3 phases. So the first phase of the development up here was the true new urbanist development. It used sustainable design, neighborhood design principles, and green buildings. Through a series of institutional changes, the second phase of the development here was developed with only green building design and no sort of configuration considerations aligning with the new urbanist movement. And then it sits adjacent to this conventional sprawl community. So this is a nice sort of urban laboratory. And in short, what we've found is that the planned development that uses new urbanist principles is cooler. It's cooler during the day and the night. It's cooler through all seasons. And that this holds both for land surface temperature and for thermal comfort. And this is just some field work. The thermal comfort work is really just still emerging. Okay, so in sort of an idealized format, what would the interface between design and planning look like in the sort of the new urbanist and land system science worlds? Well, ideally, the new urbanists are creating these field experimental sites like the one I just showed you, kind of in line with some of the urban ecological field sites. Here's the North Desert Village, which is part of the Central Arizona Project, long-term ecological research site. And these built sites would then produce field data, which could then be analyzed using methods coming from the land system science community, and then fed back into the new urbanist community to sort of make adjustments. But that's not what's happening. What's happening is the new urbanist community in green is basically operating on its own. It's doing non-systematic evaluation sometimes, not always, of its developments to inform future development. And the land system science community is really working in large area, large and urban field stations. So I'm not trying to suggest that new urbanism is the super, super important, well, I am. I'm not trying to suggest that new urbanism, everyone should be studying new urbanist sites. What I am trying to suggest is there's a scale mismatch here. And right now, as of my talking, there are a total of 4 peer-reviewed publications actually evaluating the environmental impact of built sites. Okay, so trigger warning for those of you who are submitting NSF grants. I'm just going to share some comments that I've gotten from the NSF trying to fund larger scale versions of this work. And this is not to suggest that they're not funding me because of sort of the new urbanist link, but it is to show some of the issues that arise when you want to do work in urban systems, linking the design community with science. So in the first example, the first quote is the actual quote from one of my reviews, in which they're suggesting that I proposed a co-development model with urban planners, developers, and managers, and they're suggesting that this is going to inherently bias my work, and that I'm going to be forced to conclude that new urbanism is environmentally friendly. So I've substituted the terms community organizers and activists of community-based projects. This is a weakness because there's subconscious pressure to find positive results to show that community-based projects are improving the neighborhood. I don't know. Maybe those of you who do community-based work have run into this problem, but I think there might be something that is worth exploring. How do we co-design methods with those who can also profit from our research? Another thing is the issue of naturally occurring data inputs. There's a huge data problem. So what this reviewer is saying is that we don't have random selection because I don't have a universe. There's no such thing as a universe of new urbanist projects. The community itself doesn't even agree upon what constitutes the universe. And so there's this issue of how are we going to kind of reconcile generalizability and those sorts of research methods with the fact that our field data may be messy and may not ascribe to those sort of standards. Moreover, the new urbanist communities themselves would like smaller scale data, and that's something our presenters this morning were talking about. And finally, I'd like to just say that usable data inputs are different for stakeholders in science. So here, this is the review saying that I need to look outside of the new urbanist communities, that the performance of urban form more broadly. Fair enough. Seems to suggest this is too small, too narrow of a focus. Again, I did this little sort of substitute of language exercise. What if I said we need to look outside the RED+ approach and consider the performance of payments for ecosystem service schemes more broadly? That there's something about, we have to look at the whole governance system. I just don't think that comment would have been made. So again, we need to think about how we communicate this work in the scientific community. So in summary, there are epistemological differences between design thinking and hypothesis-driven science. There's methodological differences, mainly the scale of focus and interest. There are institutional challenges that are reinforced by the reward system. You don't see a lot of sort of small-scale, small-n case studies being published in PNAS. And the organizational culture, which I think is probably the most difficult to overcome. It's these micro-practices of sort of the daily work that systematically include or exclude and determine what's valid information. And just to end on a point of optimism, I'm a devout institutionalist, but I think there's a role for agency. We need to continue to work and to press and say it is important that we sort of bridge the design and land system science communities. So with that, I would like to introduce our wonderful panel of presenters. Our first presenter will be Yujia Zhang from Arizona State University, and I will let her introduce her talk. Thank you. So if you put this around your neck, and then you can hook it there. Okay. Does that make sense? And the pointer is on. Thank you. Nice talk. Oh, okay. Thank you.
Hello, everyone. Is this on? It is on. Oh, okay. I'm Yujia Zhang, postdoc from Arizona State University. My talk examines how urban form changes surface temperature in the city. So the topic is evaluating the effect of 3D urban form on land surface temperature using Google Street View and geographically weighted regression. Motivation of this work is land surface temperature, which represents the temperature of the bare ground surface, is directly response to incoming solar radiation, and is strongly influenced by vertical urban forms, such as trees and buildings that provide shade. However, traditional 2D land cover information from remote sensing doesn't capture this vertical structure of the city, so it doesn't adequately address land surface temperature variations in the city. On the other hand, Google Street View provides this massive street panoramas that covers most of the urban areas in the world that captures this vertical urban form. So my research questions are, first, can the vertical form information from Google Street View improve the conventional land cover surface temperature assessment? And second, if so, how does the relationship between surface temperature, urban form, and social variables vary spatially in the city? My study set is Phoenix, Arizona in US. It is well known for extreme heat during the summer. It is also center of the CAP-LTR long-term urban ecological site in the US. The population of the city is 1.5 million in year 2015. Population of the larger metropolitan zone is about 5 million. This area has a typical semi-arid desert climate. Temperature during the summer is often past 38 degrees Celsius during this long hot summer. The typical urban form in this area is open low-rise and mid-rise buildings with wide streets, which result in very high sky view factor. During the last 50 years, this area has experienced a strong and stable urban heat island effect, which greatly affect public health in this region. So in order to effectively mitigate heat in summer, it's very important to know how urban form affect surface temperature change in different places in the city. The first step is to create the 3D urban form fractions from Google Street View. This is being done using a deep learning and big data approach. So for any particular location along the street, images at 6 different directions is being retrieved using Google Street View API. Next, the 6 images were segmented into 5 different classes, which are sky, building, pervious surface, impervious surface, and tree, using a deep learning method. And finally, those 6 images were composed to a cube and then transformed to a sphere to get the 3D urban form fractions. Here is how the 3D and 2D urban fractions looks in the study area. The black line shows the boundary of the city of Phoenix. So first is the 3D fraction of the Persian sky. We can see that because of the open low-rise buildings, very abundant located in the city of Phoenix, the Persian sky is mostly above 40%. And second shows the 3D Persian tree, which varies a lot in the city, ranging from 5% to 40%. And finally is the 2D land cover map in 1 meter. It's created using a NAIP imagery and has 6 classes that match with the 3D urban fraction. The surface temperature data I use is from the Aster remote sensing imagery, one for daytime image in the year in May 2015, and one nighttime image in July 2014. The pixel size of those surface temperature images are 90 meters. In order to compare all those data together, we aggregate all the data to census block group level. There are in total 1,400 census block groups in this study area. And here shows the daytime temperature aggregation in Phoenix. So we can see the temperature ranges from 46 to 59 degrees Celsius at different census block groups in this study area. Here shows the master flow work. First is the comparison between the 3D and the 2D fractions. And second is a correlation analysis between the surface temperature and the 2 group of fractions. And next is global regression analysis for 4 groups of different variables. First is using the 3D and 2D fraction alone. And then the third group combines the two fractions together, and the fourth group adding social variables, which are population density, median household income, person Hispanic, age, and parcel construction year. And finally, the best global model will be used to run a geographically weighted regression to further explore the local pattern. The first result compares the 3D fraction with the 2D fraction. The 3D fraction has 5 classes: sky, building, tree, pervious, impervious. And the 2D fraction has soil, building, tree, grass, and impervious. From the box plot, we can see that the 3D fraction has a smaller range and variation compared to the 2D fraction. This is because the 3D fraction is biased towards street views, which captures a more homogeneous view of the street canyon, other than the entire city from remote sensing imagery. And next is a comparison of the 3 common classes of the 2 groups, which are building, tree, and impervious. For example, the 3D building represents the fraction of the wall, and the 2D building represents the fraction of the roof. So in the result, the roof fraction is 14% larger than the wall fraction, and the two has no significant correlations. So this shows the difference of the 2 urban form data set. Here shows a correlation and the global regression result. For the daytime, for the 3D fraction, the sky fraction has the strong positive effect on the daytime surface temperature, and tree has a strong negative effect on the daytime surface temperature. And for the nighttime temperature, the pervious shows a very strong negative effect on the nighttime surface temperature. So for the global regression result, we can see that the R-square of the 3D fraction are higher than the 2D fraction in both daytime and nighttime. This shows the improvement of using Google Street View on estimating land surface temperature. And if you combine the two sets together, the R-square gets further improvement. And the best model is when using the 3D, the 2D, and the social variables together. And this will be used to run the local model. The traditional OLS regression generates the same estimate for all the spatial units in a study area, which is showing here that R-square equals to 0.6. In contrast, the geographically weighted regression creates a local model for each single unit in the study area. Here, the R-square varies from 0.2 to 0.9. And a further detailed example using the 3D person tree fraction. So its OLS coefficients equals to minus 0.2. This indicates that 1% change in the 3D tree fraction will lead to 0.2 degrees Celsius drop in the surface temperature everywhere in the city. This is probably not true, since we know that the 3D tree fraction varies a lot in the city at different places. So it's very unlikely that the same increase in the 3D tree fraction will result in the same temperature change in different places at the city. And here shows the coefficients of the GWR result compared to the coefficient of the OLS result. So we can see that at different places of the city, 1% change in the 3D tree fraction actually lead to 0.1 to 0.5 drops in the surface temperature. This is very helpful for sustainable urban design because it gives us clues on where to plant trees to best reduce heat in the city at different places. To wrap up, this study used fine-scale 3D fraction and 2D fraction to estimate the surface temperature at Phoenix, Arizona. And one of the key findings is the Google Street View 3D fraction significantly improved estimations of daytime and nighttime surface temperature in summer. We found that the 3D fractions from Google Street View has smaller range and less variations compared to the 2D fractions from remote sensing. And also, the GWR model greatly improves the estimation of the surface temperature over the OLS model. R-square increased from 0.6 to 0.8. And finally, The coefficient map from the local GWR model provide place-specific information for sustainable urban design in desert cities to reduce heat. And this research is being published in Landscape Ecology if you're interested in checking this topic. The work is supported by Central Arizona Phoenix Lantern Project and the Environmental Remote Sensing and Geoinformatics Lab at ASU. Thank you.
Why did you choose to aggregate at the census block?
Oh, yeah, that's a very good question. Because the Google Street View has a different viewing angle and viewing direction. So the object in the Google Street View will change depending on its distance from the viewer. And the traditional remote sensing image is kind of this top-down bird's eye view. So in order to make them comparable, and also because the urban form is very homogeneous in Phoenix, we figure out, and also plus kind of adding social variables, which makes things easier. So we do the aggregation at the block group level.
Have you never thought about seasonality on green classification?
On the land cover classification?
Yeah, the seasonality, I mean, even before, when you classify trees, basically, seasonality could affect a lot your classification.
Yes, seasonality will affect the kind of the grass cover here a lot in Phoenix if you do a summer classification versus a winter classification. But since this work addressed mostly kind of the summer heat, so the map is created using images from during the summer, from June to September, to capture kind of the most abundant vegetation cover. Yeah.
Yeah, on that slide you show the black line. I suppose that's the limit of the city of Phoenix.
The boundary.
The boundary.
Yeah.
But actually the city looks like it extends beyond the boundary, right?
Yes, the city area is a rectangle area, kind of covers more than the city to the outside metropolitan zones.
Just a clarification then, did you use the boundary of the city for your analysis?
I actually use kind of the boundary of those block groups. That's the study area.
You didn't aggregate at the city level?
No, but I mean, if you check the city level, it also aligns with the block group boundary. Yeah. The reason I do this as a rectangle area is because for the GWR regression, it matters a lot how your kind of how the shape of your study area looks. If it is very irregular shape, the GWR don't work very well. That's why we pick a kind of the rectangle shape.
Okay, very well. Thank you again.
Thank you.
Yeah, please.
This hooks on kind of
What do I have?
so you put it around your neck first.
Okay. Thank you. I shouldn't take too much time because I have 3 minutes. Okay, so in the next 3 minutes, I'm going to take you to Singapore. Singapore is this city in the garden, and it's 40% green, but the speed of the increase in temperature is twice as fast as the world city temperature increases. And the idea behind the project is to try to find out how to accommodate the 10% more people coming in the next 8 years, and to maximize ecosystem services while having new buildings, because there's not enough room for all these people. And what we've heard before about co-design is exactly what we tried really to implement. So we designed an iterative loop between a physical design here, and I'm going to show a little bit more about it afterwards, which you can modify. It's based on point cloud technology. I'm going to show that. And it's fed into different models. And here I'm just going to show what about the urban heat island, which is which consists of different models here. We have models addressing wind speed, we have model addressing the humidity, and we have model addressing the radiative transfer. So we did this in different iterative loops with the stakeholders together to improve the design, the real design, iteratively, but informing this design with science. So you can see here how this design here can be transformed. And you can see here that depending on the design, you'll have another output into your different models. And we use this in 6 different time steps with stakeholders to try to design the final loop. And it's more than just creating informed design and creating a co-design with the stakeholders, but it's also something about creating an immersive environment which is better understandable also by the planners, and that's maybe also creating a new language for communication. So these are point clouds. They are these LiDAR data you can use, which can be modified even manually, which can be milled in 3D, and can be used directly as the physical model for all these other models. So to finalize, I would say there are still important challenges doing these kind of techniques. The first one is it looks, of course, very immersive. But as many of you know, working with LiDAR data is not that easy. And the LiDAR information is very difficult to extract. So it's very difficult to extract, is it a tree, is it a house, etc. So there's a lot of work to be done here to be much faster in transforming the LiDAR point data into a model which can be used by the science for informing, for example, about urban heat island. The second thing is we're working here in a very specific environment in Singapore, and a lot of data we are collecting are filtered, are collected and also distributed by certain agencies and do not represent the full reality. So again, using these kind of data, we have really to think what kind of data do we have, what kind of signals do we have, and who is distributing and filtering this information. And the third challenge, I would say, is it would be nice to have these things in a real time. We are at the moment able to mill it directly or to print it in a 3D, to print the point clouds. But the question is, how fast can we do these iterative loops to be really usable with stakeholders? Thanks a lot.
So these LiDAR data, are those collected by the city?
So we have mixed 2 sources. One, we've collected them with a terrestrial laser scanner, but we had big issues because we're not allowed to go everywhere. So we went on top of the HDB buildings, taking them from the top, and we stitched them together. And we linked them to some of the LiDAR data provided by the area, but we don't have it for the full Singapore because many of these areas are, they take away the pixels. So you have very large pixel and not a very dense point density, which does not allow to do these kind of extremely immersive environment. So we had really to link 2 sources of data, and it's really a challenge depending where you are, what kind of data you can get.
Is what you really want objects? In other words, do you care more about the digital surface model or the kinds of objects?
Yeah, we need both, because the objects are going to change extremely, for example, the cooling or the radiative transfer information, because you have some other colors. For example, depending if it's green, it's going to absorb more light, etc. And depending where the trees are and how the trees are, how the leaves are, you're going to have other information, and how the buildings are. So you need, on one hand, the digital terrain model, and then you need to be able to modify the trees and the buildings on top of it. So we've done both, and we try to define also what are typologies, which are better now in this environment, which have this amount of people in other designs, which are not just only the green design, but they're also the urban designs. So we modified both.
So Singapore is a relatively small place, and there's not a lot of room to generate ecosystem ecosystem services like water purification. So amongst your stakeholders, which ecosystem services or cultural ecosystem services resonated?
I mean, we are doing this whole called Natural Capital Project. This is part of it. It's a big project for Singapore, which was very interesting because it was funded against many other digitalization projects. So we got this big funding, and one of the most important thing is not only urban heat island or cooling effect, but it's this whole biodiversity, mangrove change, and the whole soil change. Because, as you know, 20% of Singapore has been built up, and one of the very important ecosystem services also, they want to do this biophilic city. And this is this biodiversity idea of these, you know, we're still in a garden, we're still in the jungle kind of idea is still very, very predominant at the moment. So you have recreation, you have cooling effect, but you have this biodiversity, these services of the parks, which are really important, and the mangroves, etc.
Have these models brought out new design ideas or planning ideas which the architects and planners haven't thought about before?
I think what it has brought is maybe not the type of buildings, but the pattern. Because it seems like understanding it at different scales, you can much better model, for example, wind, and understanding how there is, for example, a green network, a green corridor, and linking this is just part of a green corridor. It was an old train line, and linking this to this green line increases really the cooling effect of that neighborhood. And that was very nice to show them that depending how they put the buildings, that you have another general effect on the wind channels. But from the architectural, it may be also our problem because we didn't have an architect who really designed new buildings. That's another project where they put plans on the buildings, etc. That was not part of our project.
Check. So I think I have 3 minutes too, right?
Yeah, relax.
All right. Okay, while I fiddle with this microphone, please note that there is a link to this presentation. And if you get that link, then you'll have all these slides, and there are other links that you might want inside here. So if you get that link, you'll have everything that I'm about to show you. My name is Nick Clinton, Earth Engine Developer Relations. We're like the liaison between our internal developers and our external developers like you folks. I'm going to try to go really fast here because I have limited time. So I'll just introduce Earth Engine for those of you who don't know what it is. Lots of spatial information, lots of imagery from a constellation of sensors from space agencies all over the world. These are still relatively hard to get for some folks. It is Google's mission to organize the world's information and make it accessible and useful, and we see Earth Engine as the geospatial manifestation of this mission statement. How do you do it? It is much easier to move your question to the data than to move the data to you. And so the sort of the core of Earth Engine is this large archive of Earth observation data. I have to continually update this slide. It was 27 petabytes recently, but I had to change it. Scenes are coming in on a daily basis, so this is growing all the time. All that data is not necessarily useful without computation. So co-located with the data archive is a large cluster that lets you run compute using Google Earth Engine. And all the data and all the compute is not necessarily useful unless you have an API. So there is a JavaScript API that runs in a nice online IDE called the Code Editor. There's also a Python API if you prefer Python. Okay, so that's sort of what Earth Engine is and why is Google doing this. There's a whole bunch of stuff in there, but what I want to talk about specifically is the latest, greatest machine learning stuff that we're working on. And we have a lot of classic machine learning algorithms in there, linear regression, classification and regression trees, random forests, so on and so forth. But the latest, greatest hotness in machine learning is deep learning, and specifically TensorFlow, which is the Google developed library for deep learning, and that lets you do very fancy things like object detection in high resolution images if you want to, for example, count cars or predict weather on a short-term basis with very high accuracy. So we're working on integrating TensorFlow for your deep learning pleasure into Earth Engine in a very seamless way. And the way that works right now is that you export data from Earth Engine into the Google Cloud ecosystem somewhere, somehow. And once you get the data there, then you can start to build these very complex neural networks and these very complicated models. And because there's so much data in Earth Engine, you have a lot of training data, and it takes a really long time to train these models. So you have to use something like ML Engine, which is another Google Cloud service to train these models, which might take days to train. But once they're trained, then they're done, and you can get more data from Earth Engine and predict, and then bring it back into Earth Engine so you can display it. So in the notes of this slide, if you got the link, you'll have the slides. In the notes of this slide is a link to a Colab notebook on the Earth Engine GitHub repo that will let you do all this stuff. So if you can make your way to the Earth Engine GitHub repo, you'll have sort of a working example of how to do this. One of the fancy things that you can do with neural networks is convolutional methods. So not just looking at the spectral data in a pixel, but looking at a whole neighborhood of pixels, or even looking at a whole landscape. And what that lets you do is identify spatial patterns and then assemble your predictions based on combinations of the spatial patterns, and that's how facial recognition works. So, for example, you might detect a nose or an ear or an eye or a mouth or something, and then you put all that stuff together. It's the same way with remotely sensed data, except you're identifying landscape patterns, and that is still very much an area of active research. But let me just show you a couple examples. This one might look familiar to some folks in here. We collected about 80,000 data points, built or not built, was the question for the analysts, and on a per pixel basis. And then developed a model that is a convolutional neural network, but we had to do some fancy things because one pixel is not enough to train these convolutional models. You need a whole set of pixels. But if you move the one known pixel around in your kernel, then you can develop these models and predict at scale built area. So, it's hard to see. This is the United States. This is built areas in the United States. We can do this for the whole world based on this example. And that is coming soon. How am I doing on time? Okay. All right. UNet is a fancy convolutional neural network that was used to build this map of impervious surface area. Where is this? Yes. So the idea here is that this is built from a US data set called NLCD, which comes out every 5 years. There's a very good impervious surface layer there. And we can make a Landsat composite, train the Landsat composite from the NLCD continuous surface area, of continuous surface of impervious surface area. And there was a comment earlier about how, these classes don't really work in urban areas. This is a continuous variable. And then we can transfer that knowledge anywhere in the world and over a whole time series. So that will be an example coming soon into that Earth Engine GitHub repo that all of you can play with as well. And thank you very much.
Question? 1, 2, no more.
The spatial resolution of the pixel you mentioned for the map of the United States.
30 meters.
Okay, and the next one, how impervious surfaces, whether impervious or non-impervious, it's a Boolean thing, it's not continuous.
Yeah, it's percent per pixel.
So then it's not continuous, actually.
Well, right, there are 100 classes, say.
No, if the basis is Boolean, it's not continuous. Temperature is a continuous variable, increases per grid.
This is percent per pixel, not posterior probability. Yeah.
I wonder if you can just comment quickly on the differences in what constitutes built in like the United States versus sub-Saharan Africa, and how the modeling algorithms and the training methods are trying to deal with those different definitions.
Yeah, the rule was pretty simple. It's, do you see any buildings in this pixel, yes or no, kind of thing, and that was it.
Okay.
And mistakes were made for sure.
Sure.
But,
Yeah.
What about the data on the high resolution things? If you play with CNN, then the Google engine has sucks in high resolution
Yeah.
stuff?
So this example is in fact on the Users Summit from last year website, done by my colleague Christopher Brown. And this is based on high resolution imagery that Google collects in urban areas. And he released a little sample of that for this demo. You can buy those data.
All right, because a big advantage is that we can use public available data, so free data, unless if we move to high resolution things, well, the things are different as you know. Anyway, yeah, you know. It's, okay, very good. Thanks again, Chris.
Thank you.
I try to plug my laptop.
Maybe you can just take that one.
Yeah, thanks. Right. Here we go. Okay, I'm not Mattia Marconcini, I'm Emanuele Strano. Mattia is not here, he's a bit busy right now with his second daughter, so I'm taking charge of him. And well, let me go directly. I will start with a question. Okay, we are here a bunch of geographer, urban planner, and so on. Try to guess. Who is voting 5? 5. Raise your hand. 5. 1.
1.
2. 3. All right. There is no gauching. This is a sort of flat here, right? So the problem is exactly this one, that we don't have so far, in my view and in view of our team, a very precise view of the location of human settlement on Earth. So where we are, where we building, simply, then indeed the form, because since we don't have a good understanding of the location, also about the form of cities, and more than cities, human settlement in the wider sense, so whatever rural, urban, we don't need about classification now, we just need about where we live. And then also, I was mostly interested, since we don't have data, then we don't have a clear idea on how the settlement evolve over time. So how we build our human environment. So our group, that is composed by me, people at DLR, people at Google Engine, team, we, in the last 2-3 years, was trying to solving this sort of basic problem, but quite important. So, as Chris just presented, we start to, okay, the very first problem is that let's start to classify all human settlement on Earth. And together with DLR and the group of Google Engine, we developed a quite complicated pipeline in order to extract information both from temporal statistic on SAR, on radar sensor, and on the Landsat scenes. The main idea is that for a given temporal window, we are not looking only at single imagery, but we stack all the imagery in one temporal window, and we classify pixel based on the temporal statistics. So the overall idea, and over this pipeline, I just explained this because we have really short time, is that if we stack during all the scene that has been taken over 1 year, and you count the temporal statistic, the behavior of built-up environment is totally different than the rest. So this was a sort of the innovation in this pipeline. Chris, correct me if you are the technical guy. So, well, these are an example of the Landsat, and again, we combine the classification of the Sentinel-1 and the Landsat 8 through a very complicated pipeline using 20 classifiers and then giving the best rate of the classifier in the Google Earth engine. This is an example of the two layer and the final classification. Well, basically we end up with an inventory of human settlement on Earth, and the target period is 2014-2015, and we are the working unit is 1 degree. We process to 560,000 Landsat scene and 200, a lot of data processed together within the Google engine. And well, the most important things of this data set is that we managed to validate it. As you know, most of the global inventory, they just produce a good classification, let's say pipeline, and then they release the data. But most of the time, global data, especially at this scale, are not validated. So we managed through crowdsourcing, to validate all the data, over 900,000 points, basically by hand. So we propose the classification, and somebody who is telling with a high resolution imagery, yeah, that's true, that's not true. And we basically quantitatively prove that this data is the most accurate data that we can have so far on human settlement presence. Just some example, you know that we can go into the detail. This is 12-meter resolution, yes. Another example. Okay, just as a matter of curiosity, well, you know that there are some other global inventory around, the GHSL. This is the most used global inventory so far. You may have used that. This is what we propose, and this is the GOOF from released from only from SAR data from the DLR. So there are both over and under classification, especially in the GHSL. All right. So you see that the things are. Please, 5 minutes. And automated, please. All right, so answering the question, well, now we can measure it directly, and who did one? Wait, basically 1.3 is the percentage, yes, good. Is the percentage of occupied land by building. Hello? So, 2 years for having this number. Well, not only. Indeed, we can go. Please, you have a question? Okay. And not only. So we started to make some more analysis. Indeed, you know, human settlement are not distributed equally around the world. And the very basic things is that we did is start to look at the density of human settlement around the Earth, and just we divided the surface by tile, 0.5 degree. And we measure how many, the percentage of built-up surface, indeed minus water and some release mask. And we have some more insights in the location of human settlement on Earth. Well, when we have measured this percentage, we can do a sort of urbanization profile. This is simply the cumulative distribution of the number we find when we measure how many built-up is in each pixel, let's say, each cell. And we can come up with simple information, let's say, you see half of the land of the Earth surface is occupied somehow by a sort of settlement, all right? Only 0.51 is occupied by more than 90% of settlement. And this is going to be, I mean, we can read this information as the global urbanization profile. But we can even go farther. Indeed, we can do it locally and so on. The figure is quite complex, but just to give you a flavor of what we did. So when we have this pattern of settlement, the first thing also that we can measure is just the area of each patch. This is an urbanized patch. This is an urbanized what the physics do? Basically, they measure the probability distribution of these quantities. And there is a very puzzling question. When we plot the probability distribution of full areas, all right, of cities, of urban patch, human settlement patch on Earth, we are in presence of this kind of distribution. Well, if you were a physicist, you can jump on your chair. Well, there are no physicists here around. Well, I do. I always feel excited when I see a power law that is basically stable on 7 order of magnitude. And the meaning of that is that first, we don't have a maximum cities, all right? There is no drop somewhere. There is no drop whatsoever. So the maximum city size, we are very far to be reached. It is clear because there is no finite size element there. There is always a bigger town. And also that the majority of the land is occupied by a very tiny piece of occupied land. So we have a lot of information coming from this probability distribution. And the very cool thing is that strictly empirical and is global. So this is the full spectrum of the things that we can observe on Earth. And there is a poster, we can go into the detail, but really the time is too low. And another thing that we can do a bit of magic. In the presence of this kind of distribution, don't care too much about the equation. The meaning of that is that if you have this kind of distribution, you take randomly point and value in this distribution, and you can infer by a joint probability distribution the area of this settlement, the summatory of this settlement, just by the number of settlement that you pick up randomly. So let's say I am in Africa, I start to take randomly settlement around, and only by the number of this settlement I can infer the total area, because there is a strict relationship between the area and the number of settlement given the probability distribution. What that means? That we have a sort of null model, which is coming from the probability distribution of the area of the settlement. And what if we compare 10 minutes? I'm almost done. Not 5 minutes. If we have a null model, which is theoretical, and then we can compare the null model with the real data. And this is an example. So you take India, you have your nice, very well done curve, and then you take the real data. And the real data, the position and the dispersion of the real data around the null model tell us some very cool information. If this region has less or more settlement than expected. All right? And indeed, if we have much more settlement than expected, we are in a very dispersed, you may call sprawl area. If we have less settlement than expected, these places is sort of conurbanized. We may expect that any new settlement, any new pixel is just going through, connected to an already existing settlement. So this is the methodology to classify pattern of certain. Oh, what is going on here? This is Google, it's not me. It's your fault, man. Anyway, I don't know what is going on here. We had very nice pictures of all the. You may come to the poster session tonight to see that. I apologize. Okay, objective number 3. We saw the map of settlement. We saw how to measure it. Okay, about the paper and so on. And then we have the third objective: how to observe the evolution of this global settlement. Well, basically, we apply the same idea, the same pipeline, back in time. We are doing this work back in time using with the Google Engine team here in Zurich and with the DLR. And the goal is to having a very informative, let me go directly here, a very informative layer of the evolution, the yearly evolution from 85 to present time at global scale in order to, let's say, redraw the history of human settlement evolution of the past 35 years. So this is a work in progress. The data of the global data are coming available in September 2019, together with a study of evolution of human system, and together with some, let's say, a spectrum of model of urbanization that we can finally, let's say, tune and validate, because we have real data to work with. So thank you for your attention, and I apologize for the stick time and for the missing slide, and please.